Modern AI coding agents operate with extensive system permissions. To function effectively, they require direct access to the local file system, outbound network connectivity, and the active cloud credentials in the developer's environment. This access relies on an implicit trust assumption. The agent expects that standard input channels, like environment variables, local project configuration files, and deep link URIs, contain benign data. When an attacker controls those inputs, they cross the system's trust boundary. For a highly privileged tool, manipulating an input string translates directly into hijacking the agent's permission set. On March 31, 2026, the source code for Anthropic's Claude Code CLI was exposed through a debugging artifact. Phoenix Security's Purple Code Navigator program immediately initiated a targeted security assessment of the extracted codebase. The audit confirmed 3 distinct command injection vulnerabilities. Attackers could execute arbitrary code through the CLI's command resolution, its editor invocation, and its authentication helper subsystems. Because the agent holds the developer's full access rights, these flaws bypass the need for local privilege escalation. They act as direct remote code execution vectors. A single technical pattern connects all 3 of these vulnerabilities. The application passes unsanitized external input directly into a system shell. In a Node.js runtime environment, developers often use execution functions like execa or exec-sync, configured with the shell true parameter. This passes the entire string to /bin/sh-c for evaluation. The shell interprets system meta-characters like semicolons, pipe symbols, and backticks as executable instructions. Instead of reading the string as raw data, the shell actively evaluates these characters and alters the execution path. This insecure pattern is a common developer convenience. Enabling shell interpretation makes it easy to string multiple commands together without writing complex argument parsing logic. Passing unsanitized input into shell-evaluated execution contexts compromises the agent's security boundary. The application loses the ability to distinguish between legitimate system commands and attacker payloads. The first vulnerability, identified as vuln01, sits inside the CLI's terminal detection module. When the CLI processes a protocol URI, like a deep link from a browser, it triggers a handler that reads the terminal environment variable to determine where to launch the interface. The module takes the exact value of that environment variable and passes it into a Node.js fallback function that executes the system which command to locate the binary. An attacker exploits this by injecting xterm, a semicolon, and a secondary command. The shell evaluates which xterm, hits the semicolon, and executes the injection. By attending a hashtag, the attacker comments out the rest of the legitimate script, executing cleanly. Notice that this path requires 0 user interaction. The injection fires the moment the application attempts to read the environment. Attackers can control this variable through several indirect channels, such as a poisoned.env file committed to a repository, or a malicious IDE workspace configuration file that sets local terminal profiles. Assuming an environment variable will only ever contain a safe binary name creates a direct boundary failure. The second vulnerability exists within prompteditor.ts, the utility responsible for launching external text editors. The code uses a function named exec-sync depreciated to construct a shell command. It takes the target file path and interpolates it directly inside a set of double quotes. Wrapping a variable in double quotes is a common technique developers use, believing it acts as a sandbox that forces the system to treat the contents as a literal string. The POSIX shell specification, section 2.23, explicitly contradicts this. While double quotes prevent word splitting, they preserve the special meaning of specific characters. The $, backticks, backslashes, and exclamation points are exempt from double quote protection. This means command substitution syntax is evaluated by the shell, regardless of the quotes surrounding it. If a developer clones a repository containing a file named with command substitution syntax, the exploit triggers the moment they invoke the CLI's editor flow on that file. Applying visual string boundaries in code does not override the operating system's underlying shell parsing rules. The third vulnerability exists in the agent's authentication subsystem. The CLI relies on configuration helpers, like API key helper and AWS credential export, to manage tokens. These values are executed as shell commands to retrieve credentials dynamically. Because these helpers are part of the authentication process, they run before the agentic loop begins. They execute entirely outside the core permission engine and sandbox boundaries. In interactive mode, the CLI mitigates the risk of malicious project settings by prompting the user with a workspace trust dialog. The user must manually approve the execution. However, organizations frequently deploy these agents in CI/CD environments. To accommodate headless automation, the CLI includes a non-interactive -p flag. When executed with the -p flag, the agent intentionally skips the trust dialog entirely, assuming the automation caller has already vetted the workspace. Building convenience features for automation strips away the only interactive security gate, turning untrusted configuration files into active weapons. Running vuln03 in a headless CI/CD pipeline exposes the maximum impact of the vulnerability. To evade detection, the attacker crafts a payload that outputs a fake credential-shaped string. The CLI processes this string and attempts to authenticate, masking the underlying activity. While the CLI handles the fake credential, the injected payload simultaneously executes an HTTP post command in the background. This background process reads the runner's full environment, capturing cloud credentials, SSH keys, and deploy tokens, and transmits the data to an external listener controlled by the attacker. The CLI eventually recognizes the fake credential is invalid and prints an authentication error, but the post request has already completed. The exfiltration happens before the application processes the failure. A local command injection flaw becomes a silent, asynchronous network exfiltration engine. In their response to the assessment, Anthropic stated that the helper behavior is by design, comparing it to Git's credential.helper functionality. Git's credential helper has required over 7 separate CVE patches since 2020 for this exact class of vulnerability. Git has since added specific input validation protections that the Claude CLI currently lacks. Furthermore, a compromised Git credential helper typically yields a single repository token. A compromised CI/CD runner exposes the entire cloud infrastructure, artifact registries, and production deployments. An attacker does not need direct access to the pipeline to trigger this. They simply submit a pull request containing a modified .claude settings.json file. When the pipeline checks out the branch, the payload executes. This vector bridges the gap between a standard repository configuration file and production cloud infrastructure. As AI agents integrate deeper into system operations, traditional assumptions about trust boundaries and safeguards break. Relying on user prompts or configuration file trust for a system-level agent creates a massive opening.